Good morning. So today we are going to discuss about the last module of this particular course, that is the alternative routes of iron making. So under this alternative routes of iron making, we have three different topics are there. One is the coal-based DRI process through rotor kiln. The other one is gas-based DRI process, where we are going to discuss about the matrix process, as well as the smelting reduction process, where we are going to discuss about Corex method. So we'll start with first the coal-based DRI process through rotary kiln method. The raw materials which are required for coal-based DRI process is pellets, the iron ore pellets, which is of in size around 5 to 20 mm, and coal, that is a fuel, bituminous nature, and it is size is of around 3 to 20 mm. Then you have dolomite, which is of size 2 to 8 mm. And these pellets, whatever we are using, it should have the Fe total minimum 64% should be there, and the Al2O3 plus SiO2 content should be up to 5 to 6% maximum, and the tumbler strength of tumbler index of this particular raw material should be of greater than 88%. So these are the prerequisites for the to charge these raw materials into the rotary kiln. And then the next raw material, that is the flux, is dolomite, and the approximate composition is something like this. Is having a CaO should have a 28% minimum, MgO 18% minimum, SiO2 around 4%, it should be up to maximum 4%. And then you have the size range of this dolomite, as I mentioned, is 2 to 8 mm, and the MgCO3 plus CaCO3 content in the dolomite should be of 80%. And then the other raw material, that is coal. So here we are using non-coking coal, which is the bituminous grade. And the fixed FC, that is the fixed carbon, should be minimum 55%. And volatile matter should be roughly around 24% maximum. Ash, that is also approximately 21% maximum. And it should have a moisture percent 9% maximum, and sulfur up to 1%. So this is how the chemistry of the raw material should be. These kind of raw materials are preferable to be used as a part of charge in the rotary kiln process. And if you see the preparation of the pellets, whatever are using for as a part of raw material in the rotary kiln process, these pellets are basically prepared from iron ore fines of less than 5 mm size, and these 5 mm size pressed iron fines are added with bentonite binder. They're the pellets, and the purpose of addition of this fluxes, that is limestone or dolomite, that is the main purpose is to take care of the sulfur content. And for 1 ton of DRI, produce 1 ton of DRI, we should have at least pellets of 1.45 ton, and coal is of around 0.75 ton. Dolomite approximately 50 to 60 kg. So we should use to produce 1 ton of DRI. Raw material, whatever we are charging, should be of this proportion. And this is the schematic diagram of coal-based DRI process. So you can see the rotary kiln, and these are the raw material which we are charging in the kiln. And this is the combustion chamber. Then you have a waste heat recovery boiler, and you have electrostatic precipitator, and then you have a chimney of the. So this is the schematic diagram of the coal-based DRI process. Yeah, so these are the bunkers which are used for the raw material. One is used for the iron ore, other one is used for the coal, as well as the third one used for the dolomite. These are called as debins. One debin contains around 12 such kind of bunkers will be there, approximately. And about the rotary kiln, the length of the kiln will be of around 70 meters. The length of the kiln is around 70 meters, and its dia is around 4.2 meters. That is without castable. And with castable, it is of around 3.8 meters. That is the working volume of the rotary kiln. And especially, we use low cement castables, that is of LC45 at the inlet end of the kiln, and LC80 that is used at the other end of the kiln. And this 45 means is the amount of Al2O3 content. And we can see the chemistry of these castables which are used in the kiln. And these castables basically are mixed with water in the mixer, and the slurry is basically tested on the shell part, and that we will be having the anchors which are fixed to shell parts that act as a reinforcement, and on that you just used to paste this castable mixer and allow it to dry, so that it will be dried, and that will act as a lining, refractor lining inside the rotor kiln. You can see in this particular slide, this is the mixer is used for the preparation of the castable slurry, and these are the anchors which acts as a reinforcement, and on this you apply the castable mix, the slurry mix, so that it is just like acts as a matrix in the reinforcement kind of system, where after solidification, after drying, it will be like this. Inside, it will be gas will be like this. And the size of these castable blocks will be of around 600 mm to 600 mm, and thickness will be around approximately 230 mm. And this kiln will be rotating at an RPM of 0.36, and the capacity of the kiln is approximately 300 tons. The dimensions of these kilns may vary, or parameters may vary from plant to plant. And the length of the kiln, if you see, it is of around 70 meters approximately. And the 70-meter length kiln is divided into 9 different zones, starting from the inlet to the discharge side. And there will be 9 thermocouples are inserted at 9 different zones of the rotary kiln to measure the temperature prevailing inside the kiln. And this rotary kiln also, it is inclined at an angle. That is around the angle of inclination, or the angle of kiln, is 2.5% of its total length. So if the length is 70 meters, then 70 into 2.5 is 1.75 degree inclination will be there. So that the during the rotation motion, the feed, the raw material will travel from the feed end to the discharge end of the kiln. And for the first time, when you want to start the kiln, certainly the kiln is basically fired with diesel, and the burner contains glass wool to lighten the fire. And if it is fired till the temperature of the kiln reaches to a temperature of around approximately 500 degrees centigrade. And once the temperature is reached, then the butter metal is basically charged into the kiln. So this firing will be done from the other end of it. So here we basically use feed pipe blower. So the purpose of this feed pipe blower is to compress the outgoing gases. You can see here, this is basically called as a feed pipe blower. So this is the charging side, and this is the discharging side of the kiln, where you have a cooler end will be there. So we use the feed pipe blower so that whatever the outgoing gases which are there, that will be compressed, so that it will be traveling in the right direction rather than going outside. So whether the pressurized air is sent to that, so that will oppose the outgoing CO gases into the ambient atmosphere. Okay, so when you use this feed pipe blower, because of we are trying to compress it, so that we are allowing the waste gases to flow out of this kiln into the ABC chamber. So the pressure of around 6 to 8 bars is maintained at the inlet end of the kiln. So this is you can see this part, this particular circular part, whatever it is, that is the inlet. This part, that is the inlet part of the kiln, and here you will be having a tube. From this particular hole, there will be tube. Means this part, this tube part, whatever it is there, that will be basically inserted from here. Okay, so in this picture, actually, during the maintenance time, this tube part is basically removed. Okay. but generally it will be inserted from this particular hole and into this particular kiln. This is the inlet of the kiln. The mouth of the kiln you can clearly see. Then we have some of the accessories like a tip cast. Um, this tip cast has actually inserted here. You can see this is called the tip cast, which is basically inserted at the beginning. This tip cast is basically um, uh, hang with the chains, uh, and that will be inserted into the kiln, mouth of the kiln. So that from this through this tip cast only the raw material will enter into the enter from the chute. Means it acts as a an passage for the raw material to enter from the chute part into the kiln. So basically, the raw materials are stored in the silos, and these silos are roughly around 3 ton capacity. And before we charge this raw material into the rotary kiln, a weighed amount of raw material are taken onto the conveyor belt, and that through the conveyor belt, these raw materials will be charged into the rotary kiln. So this is the other end of the kiln, where you have a kiln outlet. This is the kiln outlet. So here you can see at the kiln outlet, where you have a whole inlet system is there, and you have a central burner fan is there. This is the central burner fan, and this is the coal inlet pipe. The same thing you can use it here also. You can see it here also. This pipe is whatever it is. That is this pipe is used for the injection of coal, and this is basically um, this coal with the help of some pressurized air. It will be pumped into this kiln. So basically, this coal is injected into the kiln from both the sides, from the inlet side as well as from the outlet end of the kiln. Uh, and the outlet will be having a coal of different sizes, around 5 to 20 mm size, as well as fines of less than 6 mm size. So both these size fraction of the coals are injected into a DRI as a fuel to the apart from this, the air is injected at the kiln outlet by means of this central burner, so that it will be the combustion process can take place effectively. So this is the lighting up procedure of the kiln. So when you're at the beginning stage, when you want to start a newly lined rotor kiln, or when you want to start the shutdown kiln, then this is the step-by-step procedure which uh, the operators will follow. Light up of the kiln, that is the first for the first time when the kiln has to start. When the kiln is fired with light diesel oil up to 36 hours, and the burner contains glass wool to lighten the fire. It is fired till the temperature of the kiln reaches to 500 degrees centigrade in the discharge end. After that, we supply injection coals from discharge end to sustain the temperature. So once the temperature of around 750 to 800 degrees centigrade is reached, then the feed coal, means that is from the inlet end, feed coal is fed into the rotor kiln. That is called as feed coal. And apart from that, other raw materials like iron ore, dolomite, those are also will be charged from the feed end of the rotor kiln. Then, if you see the raw material charging proportion, iron ore, various raw materials like iron ore, coal, and dolomite are fed in proportions from the feed end. And the injection coal fines are injected from the outlet that we have already seen here. And around 40 to 45% of the total coal is charged from the feed end part, and the remaining around 55 to 60%, whatever it is there, that will be charged from the discharge end by pneumatically. The amount of fluxes, whatever we are adding, is purely based upon the amount of iron ore which we are charging into the rotor kiln. So approximately this will be based upon the iron ore content. So around 2 to 4% of iron ore, that much quantity of fluxes, that is dolomite, is basically charged into the your kiln. So you can see the amount of raw material which we are charging into the kiln. At the burner end of the kiln, the injection coal, that is from lumps, that will be approximately 4.5 ton per hour. That is the, as I mentioned here, this part, that is the 5 to 20 mm and 6 mm. So these coal fines at the burner end of the kiln, they will be charged at this rate. At the charging end of the kiln, if you see that the feed coal will be of around 2.84 ton per hour, and iron ore is around 20.45 ton per hour. This is as per our plant data. It may be varies from a plant to plant. And dolomite, approximately they are charging 0.38 ton per hour. So the coal, basically whatever we are charging, that acts as a reductant as well as a heat producer. So the coal, whatever we are adding from the inlet, is used for the direct reduction of ore, and coal fines along with the AAVs, whatever we are adding discharge end, that also acts as a fuel to generate the heat for this particular process. So this is basically one kind of countercurrent process where the hot gas will flow over the solid bed in the countercurrent direction. And we have a great space freeboard. It is called freeboard inside the kiln for this reaction to take place inside the rotor kiln. So around 1/3 carbon will enter into the kiln from the feed end, and approximately 2/3 of the carbon will enter into the kiln through the burner. The rotation of the kiln removes the surface area of the ore as well as the kiln surface to the hot furnace atmosphere, which is enhancing the heat exchange and kinetics of the process. Rotation and inclination of the reactor also helps in forward movement of the ore under gravity. So as I already told you previously, that the inclination, whatever we are maintaining, that will helps in inclination as well as rotation. So these two will help in the movement of the butter inside the kiln. So around the length of the kiln, there will be some ports are arranged through which the secondary air is injected for the post combustion of CO into the kiln in a controlled manner through these shell air fans. You can see here shell air fans, and these fans basically do the suction of air from the ambient atmosphere, and then it will be sent to the rotor kiln. And inside the kiln, the air will be passed through these air tubes. Okay, so these tubes are fixed to this kiln, and this will be fixed and phased such a way that opposite to the these air tubes, that is the flow of the air will be opposite to the movement of the button inside the kiln. So if the button is moving from the charging end to the discharging end, then this phase the outlet of this air tube will be aligned in the opposite direction of the flow of the button inside the kiln. And as I said, it is a rotary kiln. This kiln rotates at certain RPM, and that rotation is basically supported by the supporting rollers. And this is a kiln tire. This is a kiln tire, and that is supporting rollers. So on this kiln will be rotating. So this picture basically shows the cross-sectional view of the kiln. As I said, you can see the amount of raw material which is fed into this kiln is very means the volume occupied by the burden is very less, and you have a great free port spaces there. So hardly around 15% of the total volume is occupied by your burden. Here you'll be having the temperature which is prevailing inside this kiln will be approximately around 1000 to 11 degrees centigrade. And it should not exceed more than 1050, the temperature. So that to avoid this ash fusion holes and the accretion formation inside the kiln. So we have to operate. That's why we operate this kiln at a low temperature, because to avoid this accretion formation. Because when you know the ash fusion temperature of the coals, so below that temperature only we should run these kilns to avoid this accretion formation and all. If you see the various zones in the kiln, as I told, that length of the total length is divided into 9 different zones, and out of which approximately every 3 zones will be converted considered as again these 9 zones is again divided into three zones. One is the preheating zone, the drying zone, preheating zone, and the combustion zone, like that. So preheating zone, if you see in this zone, the moisture in the charge is driven off, and the volatile matter in the coal will be liberated out of the kiln, out of the coal, and temperature which is prevailing inside the kiln will be around 600 to 800 degrees centigrade. And in the combustion zone, the charge material will be preheated to around 950. Whatever it is there, the preheated charge will enter into the combustion zone and exposed to temperature of around 1011 degrees centigrade, which is approximately solid reduction reaction zone. And the heat from the combustion rises the temperature of the lining and the bed surface also. As the kiln rotates, the lining will transfer the heat to the charge. And because of this behavior, these kind of solid reduction reactions may take place inside the kiln in the preheating zone as well as in the combustion zone. So in the preheating zone, you can see there is a certain transformation of Fe2O3 to Fe3O4 is taking place. Fe3O4 to FeO taking place because of reaction with carbon monoxide gases. And in the combustion zone, The oosterite will be again reduced to Fe in both direct as well as indirect form. And for this process to take place effectively, we are providing air of around to produce 1 ton of DRI. That we are providing air of around 1950 Nm cube and power of around 1.5 kilowatt per hour. And heat is around 16 to 23 gigajoules. This is to for 1 ton of DRI. So the entire burden, whatever you have charged inside the kiln, that will take around 10 hours to move from the inlet zone to the discharge zone of the rotor kiln. And approximately based upon its length of the kiln, our kiln length is around 70 meters we have taken. So approximately the charge or the burden which moves inside the kiln is at a rate of 7 meters per hour. That is for this 10 hours, 7 meters per hour to 70 meters. So in 1 hour, approximately 1 hour, around 20 to 30 tons of DRI will be transferred from the kiln to the cooler drum. This is the cooler drum. Whatever the DRI which are produced in the kiln, the DRI will be transferred into the kiln because we cannot, because these DRI, whatever it is produced, is of very high temperature, and we cannot, unless until you don't cool it, we cannot handle this DRI. Because at high temperatures, there is a possibility of burning of these conveyor belts may take place, and also the exposure of this DRI at high temperature to the ambient atmosphere may lead to again reoxidation, reoxidation of this iron-bearing material. So to avoid that, we do indirect cooling by using water sprinkling on the surface of the cooling drum, so that indirect cooling will take place, and then the temperature of these DRI will be reduced to around 100 degrees centigrade. So this is the inclined plate is inside the kiln, and through this plate, the whatever the DRI is there, that will be transferred to the means this plate is actually present between the kiln and the cooler. So through this plate, actually the raw material, the DRI will be transferred to the cooling drum. And at around 1100 degrees centigrade, the DRI will be transferred into the cooling drum. And if you see the dimensions of this cooling drum, it is of approximately 35 meters in length. And as I already discussed, the kiln will be of around 70 meters in length. So total, if you see the entire process, both kiln as well as the dryer, it will be around approximately 105 meters. So this cooler is also inclined at 0.5 degrees and rotates at a RPM of 0.3 to approximately 1.2 RPM. And the residence time of the charge inside this cooling drum will be of around 2 to 3 hours. So as I said, in the residence time of the DRI in the kiln is around 10 hours, and here around 2 to 3 hours. So roughly around 12 to 14 hours of time takes for the DRI to discharge cold DRI in cold DRI form. So the next continuation of this topic we'll discuss in the next class.